Welcome to Net Change Part 3. Another particle motion. This time all my answers are written up here, so I have to squeeze them in. Well, I squeezed them in, but I squeezed them in previously. All right, so particle motion, and I typed some of them. A particle P moves along the x-axis. Its velocity, v of t, is given in the graph below for the interval. Sorry, the box that says screen recording is blocking me a little bit. 0 to 7. It's given that s of 0 is 5. So we have an initial position, right? So it means that when the particle set is 5 when t equals 0. All right, so notice, by the way, a of 2 is undefined, not differentiable. We have a sharp corner there, right? So we have an undefined acceleration at t equals 2 seconds. All right, so we're asked to find s of 3, v of 3, and a of 3. All right, so to find s of 3, we find the area under the velocity curve for the first 3 seconds. All right, and that gives us our displacement. All right, so from 0 to 2, you see we got a triangle there. So that's going to be 2 times 4 divided by 2, that's 4. And then we have a trapezoid, that's going to be 2 plus 4 divided by 2 times 1, that's 3. Well, I have s of 3 equals 12. Where did the 12 come from? Well, we have to add in the initial position, right? So it's the position is going to be our displacement plus initial position. So as you can see right underneath the graph there, s of 3 equals 12. 4 plus 3 plus 5 gives us 12. So right there where my pen is trying to write. V of 3, all right, all you have to do is go to where it's 3 and just follow right up. All right, so 2, whoops, all right, it's at 2, right? Because if we just follow up the graph, you can find the y coordinate, no problem. All right, so a of 3, all right, so that's finding the slope of your velocity. We have a negative slope, and it appears to be about -2, right? That from 3, right? If you notice, look at that, from 2 all the way to 4, right? That's a slope of -2. So a of 3 is going to be -2. When's the particle moving to the left? Well, when the velocity is negative, so from 4 to 6. So here I have all my becauses below, right? My justifications. I have my answers above. When's it moving to the right? It's moving to the right from 0 to 4 and from 6 to 7 seconds. And then so if you look below, the particles moving to the right where velocity is above the x-axis, we have positive velocity. Particles moving to the left where velocity is below the x-axis, negative velocity. Make sure you justify your answers. All right, and now when does P change direction? Right, it's going to change direction where velocity goes from negative to positive or positive to negative. All right, so you got to hit 0 and then go in the other direction. So at t equals 4, we go from positive to negative. At t equals 6, we go from negative to positive. So we changed directions there. Find the position of the particle when it's farthest to the right, the absolute maximum, and farthest to the left. Right? All right, so absolute maximum, all right, notice it's going in the positive direction. So it goes 4 in the positive for the first 2 seconds, and then it goes another 3, and then it goes from 3 to 4, it goes another 1, right? So now it's up to 8, and that's it, all right? Now I'm going in the negative direction. And this positive over here will not overcome this negative over here. So after that, the total would be, we go negative 1 and then a positive 1/2. Right? So the farthest we ever get is at t equals 4 seconds, because then we're moving in the negative direction, and even when we turn back, we don't make up the part that was it was in the negative part. When are we farthest to the left? Well, the farthest to the left we get, let's see. So we start off at 5, right? Did I write down moving the positive? I don't think I wrote down where it's most to the left. Anyway, we can look at the graph. All right, and we'll find where, if it's up here, I don't know where it is. You can read through that. So when it's farthest to the left, right, it starts off at 5, right? That's its starting point. And since we're moving in the positive direction, we just keep adding, and the negative we take away won't make a difference. So the furthest left it ever is 5, right? Our starting position, because after that we're going mostly positive. All right, that's our absolute minimum was 5. Our absolute maximum was 8, right? Because this would just take away, from 4 to 6 would just take away 1. So then I'd be at 7, and then I'd be at 7.5. So farthest to the left we ever are is a starting value at 5. All right, and then find, and I think we've answered all the questions. Right? So some other information, your absolute max and min always occur at your critical points or your end points. In this case, it was the end point. It occurred, one of the end points occurred at 0, was our farthest left, and at a critical point, we know it's a critical point because our the derivative is 0, right? T equals 4, our derivative is 0, so that would be a critical point, and that's our absolute max. And let's move on. By the way, I have the same thing over here without all the writing. Oh, and what's this? All right, so actually let's look at the graph. So the graph here, this is showing the position function. Almost forgot. So this is the position function. So we start here at 5, right? And then we're going positive. We got a positive 2 for that first little triangle there. And then we add in another 4 over here. That would be for the trapezoid, or 3, excuse me, add another 3. That would be for the trapezoid. So now we're at 11, right? And then we're going to add in for that triangle there, we're going to add in another 1. So now we're at 12. Right? And then we start, so we start at 5 plus, excuse me, that's 4. So for the first, the first second we're only here, looking at 2 seconds. So for the first second we add just 2. So for the first second we go up to 7. For the second, right, that's where we add in the 4, so we would go on to 11. And then for the next second, we're going to add in another 3, so we'd be at 14. And then after that 4th second, we're not going to add in anymore. We're going to be decreasing. Okay? So that's the graph there of our function. A little choppy, but we're just taking the areas to find our positions. And that's what you do to be able to graph the position function from the, I probably should use this one, I can see it better, from the area. These are in your notes, excuse me, the position function from the velocity function. These are in your notes, and I have them covered up because I want you to kind of think of what to do or what the answer would be before I show you. So they're not written in, so you'll have to write them in. These are very much like FRQs on the AP Calculus test. If W, there's a prime symbol in there, I don't know if you notice it. So, all right, so that's the derivative. If W prime of T is the rate of growth of a child in pounds per year, and if we think about it, derivative gives us the rate of change. So that has to be the derivative. So rate of growth of a child in pounds per year, what does W prime of T dt from 5 to 10 represent? So either write it down or in your mind or put on scratch paper. Or pause the tape. What do you think that means? All right. So write down what you think. Pause the tape. Write down what you think it means, so you can kind of check yourselves. You know, how are you doing on this concept, or do you understand it? And then were you right? Were you wrong? I think it'll help you remember it more if you try and answer it first and then you check yourself. All right. So I'm not going to wait around for you to answer. I'm just going to let you pause the tape because you can do that, and then you can have as much time as you want. I'm just going to show you the answer. is the total rate in growth from ages 5 to 10 years, right? So when we integrate and evaluating, we're finding our total change in the original function. So if this is the rate of growth, is the derivative, then the growth, right, is the original function. And so it's the total change in growth from ages 5 to 10 years. All right, number 5. Oops. If oil leaks from a tank at a rate of RT gallons per minute at time t, what does the integral from 0 to 120 RT dt mean? All right, so pause the tape, right, see what you think it means, and then I'm going to show you the answer. And I would definitely write in these answers afterwards. All right, welcome back. It's the total amount of oil in the gallons that are leaked in 120 minutes, or 2 hours, whichever you prefer, right? Because this is a rate. So and when we integrate and evaluate, we get the amount, right? So this doesn't just work for going from velocity to finding the position traveled. It also goes from other things, from other rates, to find the total. That's why this lesson is called net change. So we can find net changes in other things. So this is the total amount of oil that's leaked. A honeybee population starts with 100 bees. What does 100 plus the integral from 0 to 15 n prime of t dt represent? All right, so pause the tape, come up with your answer, and then check yourself. All right, so the answer is the total number of bees after 15 weeks, right? Because we started with 100, and then we add our displacement. We add our change in bees. So that's going to give us the total number of bees after 15 weeks. All right, so anytime we integrate and evaluate on our definite integrals, we're getting our rate of change. And this one, I didn't put in, a lot of these I'm going to put in a blank and have you figure out your answer and then show you the actual answer, except for this one because the graph is a little confusing and I don't remember if it's in your notes. The graph is confusing because it's the wrong graph. Either the wrong graph was placed with this initially, or which I think is what happened, or something. And the reason it has to be the wrong graph is because it's the wrong units. So this is looking at gallons, and that has miles. So, well, that just doesn't work. So we're just change that a little bit. So it's gallons per minute, not meters per second. So water is leaking out of a tank at a rate of RT gallons per hour, where T is measured in minutes. So I put minutes up there instead of hours because it doesn't match the graph, right? It doesn't make any sense to be in hours. So this question had some problems with it. It's a practice AP problem. It just had a couple problems with its units. So that should have been minutes. And then see graph of R of T shown here. And that's the graph. All right, so we want to write a definite integral that expresses the total amount of water that leaks out in the first 2 hours. All right, so here, since this is minutes on our graph instead of hours, use minutes. But that is what they're looking for, that you can recognize that you take the derivative and you can recognize what the endpoints should be, the starting and ending, and don't forget your DUT, your variable of integration. And that's all you need to do for that question. On the graph here, shade in the region whose area represents the total amount of water that leaks out in the first 2 hours. Right? So that means we're going to go to 120, and we're going to shade that in, and then we can, it's a trapezoid. We can find the area under the curve. Okay? So to find the area under the curve, we would just add, it's a trapezoid, 70 plus 120. The height of that is 40 divided by 2. So 3,800 gallons. So we're using area under the curve to evaluate our integral and find our total. Give an upper and lower estimate of the total amount of water in the first 2 hours. So if they ask for a question like this, I didn't solve this one out, but if they ask you a question like this, an upper and lower estimate, okay, so you look at the graph, it's either going to be a left or or a right Riemann sum. So if they ask for both, one of them is the left and one of them is the right. If it's an increasing function, then the left gives the lower estimate and the right gives the under estimate. If it was a decreasing function, then it would be the reverse, right? So then you just do a Riemann sum, break this thing into rectangles. And if it doesn't tell you how big the rectangle should be, well, then you get to decide yourself. All right. So let's move on. A cup of coffee at 90 degrees is put into a 20-degree room where T equals 0. The coffee's temperature is changing at a rate of R of T equals negative 7e to the negative 0.3 T degrees Celsius per minute with T in minutes. Find the coffee's temperature when T equals 10. All right, so now we have a couple questions that we're going to answer here. All right, so the first thing is we have to, this one was a longer question. It wasn't like the A, B, C, and D's. So this time I didn't say, okay, what do you think you're going to do? So remember the 90 degrees is your starting temperature. All right, so that's going to go, you're going to add that to your displacement. How do you find your displacement? You're going to integrate and evaluate. All right, if it says find the coffee's temperature when T equals 10, means you're adding up all the little infinitesimally small rectangles from 0 to 10. All right, make sure you know that you start at 0. All right, if it says when T equals 10, it means you have to add up everything from 0 to 10. Negative time has no meaning, so we're not going to use negatives. Make sure you start at 0. Don't just try plugging in 10. All right, it's the accumulated chain, all the accumulations till you get to 10, right? When we were evaluating on those graphs, S of 3, right? S of 3, right? So the total change, the position at 3 seconds, we didn't just like look at 3, we had to add up everything from 0 to 3. So you have to add up everything from 0 to 10. So I want to make sure that's very clear. So our variable of integration is from 0 to 10. All right, so I need to do a U to U substitution because I have something that I have a problem with the variable there, with the exponent, because it's not just a t, right? If it's not just a t or an x or whatever, do a u to u substitution, all right? So u equals negative 0.3 t, du is negative 0.3 dt. I don't have a negative 0.3 in the equation. I'm not worried about the 7, I just pulled it out. So I'm going to divide everything by negative 0.3, all right? So now notice that I pulled out that negative 7. So now when I do the u to u substitution, I pulled out the 3 as well, so, and the negative. So, and you can't really see the negative, but it's that dot next to the 3. So the two negatives will cancel. So now I have 90 plus 7/3, and we integrate e to the u, which is e to the u. Now, if you don't want to have to substitute back, change the limits. That's what I do. I just change the limits. So to change the limits, you're going to substitute 0 and 10 into negative 0.3t, because that's what u is. So in terms of u, negative 0.30 is 0. And in terms of u, negative 0.3 times 10 is negative 3. So the new limits are now from 0 to negative 3. I find that easier rather than plugging back in. You'll get the same answer, but it's easier. So we have 90 plus 7/3 e to the negative 3. I'm just evaluating now, minus e to the 0. All right, so now it's a calculator problem, except e to the 0 is 1. All right, so now you just plug that into your calculator and add it together. And by the way, negative 1 is greater than e to the negative 3. All right, and so there we go. So the temperature, notice it's decreasing, which is what we expect. If you leave a cup of hot coffee sitting there, it's not going to stay hotter. It's not going to stay the same temperature. So the temperature is now 67.828 degrees, which is way too cold to drink if you ask me. All right, so if you have questions on this, this is a very typical type of problem on FRQ. At least they'll have at least one of these like this. Or one of these types of problems I'm going over right now. All right, let's look at the next one. A multiple choice question. It'd be real bad if you just guessed on this one, because we want to solve it out. The rate at which water is being pumped into a tank is RT equals 20E to the 0.02T, where T is in minutes and RT is in gallons per minute. Approximately how many gallons of water have been pumped into the tank in the first 5 minutes? So I don't really want you to solve it all out. But tell me, write down, what would you do to solve this out? Real quickly, what are the steps we would take? Because when you do that, you're really thinking about the problem. Okay, so take a moment and do that. And then I'm going to show you what you're going to do. Well, we have a rate. Hopefully, remember that the rate is the derivative. And I'm going to integrate to find the total. If I'm looking for how many gallons or how many anythings, I'm going to integrate my rate of change and evaluate. So I have 20e to the 0.0t. It's a u to u substitution, right? So I've got, I left the 20. I could have just left the 20 over here, or I could put the 20 over there. Either way, the 20 is staying in this equation. The u is going to be 0.0t. Sometimes I just include the constant over there as well, because now I see that 20 divided by 0.02 is going to be 1,000. So I could just put 1,000 e to the u instead of putting 20 divided by 0.02. But it really doesn't matter. So u is 0.02t, the exponent on e, and then the derivative of that is 0.02 dt. So that means I need to divide by 0.02. So 0.02 du is going to replace dt. The 20 stayed, and the 0.02 t was replaced with u. 20 divided by 0.02 becomes 1,000. So we integrate, we have, oh, and by the way, so it's how many have been pumped into the first 5 minutes. You're evaluating from 0 to 5, right? So we have 1,000 e to the u. And I either need to plug back in or do it or change the integral. So for some reason I decided to not just plug it back in, go back to the t's. I don't know why I did, maybe just to show you something different. So w equals 1,000 e to the 0.025. So either I got to replace the u there with the 0.02 t and then evaluate that, or I have to plug in the 0 and 5 into 0.02 t. And then keep the u's and then replace the limits. So when we evaluate that, that would give us, and it's just a calculator problem, 105.17 gallons. So 105 would be the right choice there. It says approximately. It's not going to be exact number anyway. You got e in there, all right? And it's not e to the 0 power except for the last one. All right, so I'm hoping that these are making sense to you. You're seeing the, how these kind of problems are solved. Another multiple choice. The rate at which ice is melting and is given by dV dt equals the square root of 1 plus e to the t, where V is the volume of ice in cubic feet and t is time in minutes. What amount of ice has melted in the first 3 minutes? Well, I hope right in your head you know exactly how to set this up. Let's go over it. Okay, that's a rate. You're going to integrate and evaluate. All right, so you can't integrate with just the ET there. You're going to have to integrate without ET for the U du substitution. Sorry, that's what I wrote there. One of my great sentences there. So if U equals 1 plus e to the t, all right, because I got to do something. I have an expression there. Du is equals to e to the dt. I don't have an e. I have a dt, no e. So you can't integrate without e to the t for the u to u substitution. So you're going to use a calculator. You need to be able to do that as well. You still needed to set this problem up, but you also need to be able to integrate in the calculator. Because like I said, you cannot integrate every single function. How to integrate it depends on your calculator. The older calculators, I gave you the steps on the FTC. The newer calculators, it's actually easier because you just plug in the boxes. You plug in your lower, your upper, your lower, and your the variables of integration. And I think I have that calculator here. So at the end of this podcast, I think I might have both calculators. I'm going to show you how to do this on the calculator, all right? Those of you who are watching, good job, because I'm going to show you how to do this before Saturday, all right? But let's continue on. A news broadcast in early 2007 said the average American's annual income is changing at a rate. I see a rate. What does that mean? It's the derivative. Given in dollars per month by RT equals 40 times 1.002T, where T is in months from January 1st, 2007. If this trend continues, what change in income can the average American expect from during 2007? All right, so now be thinking what you're going to do. And also be thinking, what, well, if I hope you all figured out you're going to integrate. Be thinking about what would be your limits of integration if it's during 2007 and T is in months. What do you think? Of course, you're going to integrate from 0 to 12 because there's 12 months in a year, right? So T is in months and we've got 12 months. We're finding the accumulated change from 0 to 12. I pulled out the 40 because it's just a constant, and I integrated. This is a simple integration, no problem there. And I've got, so this is an exponential equation, right? An exponential. So remember, for your exponentials, you have the exact, just like e to the t, when you integrate e, you get the exact same thing, exact same copy. Same thing for all your exponentials, except if it's not e, then you have to divide by the natural log of the base. So when we integrate here, we have 40 times 1.002 to the t divided by natural log of 1.002. And that's from 0 to 12. And you just plug that into a calculator. And you get 485.80. So that's, if this trend continues, that's the change in income the average American expect. So that's what, so when they say this is a total change, that's how they get those answers, right? They have a function that describes how something is changing, and they integrate and evaluate. So that's how you, that's what you need to do to find total change, right? That's why calculus is so powerful, right? And we see we have a positive number, so hey, it's increasing. Not by very much, but it's increasing, right? That's better than decreasing. I don't know how many more questions there are on this. This is just I'm going to go over this again in another lesson, but it comes up in one of these FRQs. So the area under this graph is the distance traveled. What's the average rate of speed for this trip? Right, so total, if we take the total distance divided by the total time, we get the average. How can we use integrals to express this? So the total, remember, is the integral evaluated from A to B. The total time is just your B minus A. So this is what's called the average value of a function. I'll go over this again. The average value of the function, you're just getting the total and you're dividing by your interval, right? So multiplying by 1 over B minus A is the same as dividing by B minus A, right? That's all you have to do for average value, right? It's that simple. Really, it's a very friendly, simple formula to work with. I think this might be my last question. Well, let's find out. A faucet was turned on at t equals 0, and t minutes later, water was flowing into a barrel at a rate of t squared plus 4t gallons per minute. So how much water was added to the barrel during these 5 minutes, and what would find the average flow for these 5 minutes? Okay, for adding water, we're going to take we're going to integrate and evaluate. And so we don't have a starting value, right? It was an empty barrel. So we don't have anything to add to that. All right, so we just take t squared plus 4t dt, integrate and evaluate. So we have t cubed divided by 3 plus 4t squared divided by 2. That becomes t cubed divided by 3 plus 2t squared, and you just plug in and you get 275 third gallons. All right, and you can keep it like that or divide by 3. All right, so to find the average rate, I just take that 275 thirds, the total change, and divide by 1 over my interval. So divide by 1/5, and so 55 thirds gallons per minute. That's the average change per minute. Doesn't mean that every minute that's how much we changed, right? Because sometimes we may have more going into the barrel, and sometimes maybe it was less going in. Maybe it wasn't a constant rate. But the average change was 55 thirds. Okay, so it's really easy once you have total change. I have one more question. So I'm going to stop this tape and I'm going to come back for part 5.